Today's lesson, we're going to use functions that involve the natural base e, also known as Euler's number. So this natural base e, irrational, is defined as follows. So we say as n approaches positive infinity, um, it's approaching this function of 1 plus 1 over n to the nth power. So this n value here, as it gets closer to infinity, it's going to be approaching whatever this expression is, which happens to be e, which is approximately equals 2.718281828. And it goes on and on and on. It's kind of like pi. We denote a symbol for pi, and well, it is pi, and so that symbol represents 3.14159, etc. And so we have a new number here known as e, and this is known as the natural number. And the reason it's known as a natural number is this number shows up a lot in the natural world, and we'll discuss that more in class. But we're just going to learn how to use this with the things we've been doing in class. So here we have an example. We want to simplify these expressions. So instead of writing that irrational number, we're just going to use the symbol e. And so for a, I want to simplify e to the ninth times e to the sixth. And I can do that fairly easily, and knowing that e represents that long irrational number. So the rules for exponents still apply, so I'm just going to simply add my exponents. So the way I'm going to write this as e to the 15th power. And that's it. You don't have to plug in that irrational number unless you're trying to, evaluate that to a decimal. But most cases we'll just leave it like that as an exact term. So when I get to b here, I'm just going to take 12 and divide that into 60, which is going to leave me with 5, and then 3 minus 8, which is going to leave me with e to the 5th, and that's it. So e works just like we would treat a variable, but we know how to, that actually represents a number. So in this next one, I'm going to have, I can rewrite this as negative 10 to the third power. Remember, I'm not really distributing the exponent here. And then e to the negative 15x. Okay, so I'm going to have to simplify this further. So negative 10 becomes negative 1,000, like so. And then since this e value here is to the negative 15x, then that's going to drop into the denominator. So it'll be e to the 15th x, and that is simplified. Okay, so now let's talk about graphing. It works just like exponential functions, like exponential growth and exponential decay, except we're going to do it with a natural base. So the general form of this function is y equals a e and then r times x. And here, if my r value is, so we have this coefficient, if you will, on x, and if this r value is positive, then we're going to get an exponential growth function. And so it'll look like this, following the same rules as exponential growth that we've used before. So if I were to give you an example of what one would look like, I could say one example might be y equals a, except my a value, let's do something like 1/3 e to the power of we'll say 2x, and so that this r value is is greater than 0. It's positive. I could even include a horizontal shift and a vertical shift if I wanted to as well. So I'd have my H and K, which still applies. Here, exponential decay, if this R value is less than 0, if it's negative, like here, y is equal to e to the negative x, we would see an exponential decay, as the second graph here shows. An example of that would be like y equals 1/3 e to the negative 4x. And then again, I can always include an h and a k if I wanted to, plus 3 or something like that. But this r value you want to be careful of. It'll be either exponential growth if r is greater than 0, or if r is less than 0, it's going to be exponential decay, and then it'll look accordingly as to, it'll graph accordingly. So you should know what it looks like before you graph it, or get the general idea. Okay, so we're going to go into another formula here that you'll be responsible for. And let's say when interest is compounded continuously, the amount A in an account after T years is given by this formula, which is A equals PERT, P-E to the RT power, where E is the natural base. So here it's popping up in a interest formula. So continuously compounded, meaning like we had a compounded formula where we can choose the number of times compounded, like quarterly, monthly, daily. Here, this is continuous. It's not a set amount of time. It's just always compounding, if you will. And so P is the principal. It's our starting amount. R is the initial interest rate, again expressed as a decimal. And then again, T is our time measured in years. So let's look at an example of this one. So let's say we deposit $3,000 in an account that pays 3.5% annual interest, compounded continuously. You know it's a compound or continuously compounded formula because it will state it in these problems. So it'll tell you to use this formula versus just compounded quarterly or monthly or whatever. It'll say compounded continuously, so you know to use, A equals PERT. And what's the balance after 3 years? So the important information I can pull off of this is that I know my P value is going to be 3,000. My rate is 3.5, and we're going to do it for 3 years. So now we just substitute in, and we go from there. So A is equal to 3,000 E, and then R, our rate as a decimal, is 0.035 times 3. Now we can just enter this into our calculator. So it'll be 3,000. Okay, now to get the E, there's actually 2 places. There's one right here located above the ln. That's going to be second ln, and we'll talk about what that ln means later. And there's a second E right above the division sign. Notice one has it to the x power and one does not. Sometimes you want to use the power, sometimes you don't. Since I do have one that has a power on it, I'll go ahead and use the one with the power. So I'll press second ln. So to the power of, and I'll put 0.035 times 3. And if you have the old operating system, you'll have that in parentheses, so you have to close the parentheses and then press enter. So it's going to be $3,332.13. So I would jot that down. Let's see, which was A is equal to 332.13. So therefore you would have $3,332.13 after 3 years. So then I would box that in, and that's it. So that's the general idea of how to use functions using the natural base E, Euler's number. Until next time, I'll see you on the flip side.